Now let's make the question a little bit more complicated. A block of mass m slides down from the top of a smooth inclined plane A, which makes the angle theta with a horizontal. It then moves across a horizontal surface of length d and smoothly transitions onto a smooth vertical circular track of radius r. A. If the horizontal surface is frictionless, determine the minimum height of the incline which the block must be released to ensure that it remains in contact with the circular track all times. So for this type of question, it's still using the ideas of conservation of energy, but the most important thing for you to do is to find a point on the graph that is very easy for you to determine the amount of energy using the variables you already know. For example, in this question, I will just pick point A. So for point A, the amount of energy it has is gravitational potential energy because it's that much above the ground. I can just tell you it's 2r because there are two radius. Is equal to mg2r times 2r plus. Since it's on the circular track, right? It definitely needs to be moving. So it also have 1/2 mv squared. And EA, the amount of energy it has at point A, is equal to the amount of energy of the block has at its initial position, which is equal to energy it has at initial position is equal to mg times h. And h is the variables you're trying to find. How do we find v? The situation that it remains in contact with the top of the circle is that when the normal force at the top is very, very close to zero, right? We already talked about in a previous video. And so we can just write the net force equation at the top is just equal to mg. And it's equal to mv squared over r, right? Because there's only one gravitational force pointing towards the circle. And we can get v squared is equal to gr. We don't need to square root that for now because for the kinetic energy, there's v squared exists. So we can just plug gr back to the original function. EA is equal to, oh, this one's supposed to be capitalized R. EA will be equal to mg 2r plus 1/2 mgr, and this equals to mgh. And now we can see that these mg can be actually cancelled out. After we cancel out them, we can get h is actually equal to 2.5 r. Alright, part B. If the horizontal surface has a kinetic friction with coefficient mu, determine the minimum height on the incline from which the block must be released to ensure that it remains in contact with the circular track at all times. This is actually a little bit different from the previous part since the horizontal track, this part actually has friction. So the work done by the friction will actually cancel out a little bit of energy the object has when it's at the original position. And however, the amount of energy it has at point A doesn't change since the amount of speed it requires to remain contact with the surface is still not changed because the centripetal force is still equal to only Fg. And the height doesn't change as well. The height is still 2r. So we can just use the conclusion we get from the last part. And the energy at point A is equal to mg2r plus 1/2 mgr, and it's equal to 2/5 mgr. Now, here's a trick to solve this question. We now need to analyze the amount of energy it has at the bottom of the circular track because we can actually write two equations to express the amount of energy it has at point B. Let me explain why. The first way for you to write it is looking at this way. Since the track is smooth, right? So there will be no energy loss when the object is moving from B to A. So the amount of energy it has at point B is also equal to the amount of energy it has at point A. It is also equal to the amount of energy it has when the object is sliding down the slope and reach point B. So it will be the amount of gravitational potential energy minus the amount of work done by friction. So it can be also equal to mgh minus work done by friction. The work done by friction here would just be the friction force times d, and it's equal to Fn times mu times d. And since it's a horizontal surface, so the normal force will just equal to mg. So the work done by the friction force would just be mg mu times d. Let's plug the work done by friction back to the original function, which is over here. And this is equal to mgh minus mg mu d. And this is equal to the amount of energy it has at point A, which is 5 over 2 mgr. And you can see mg, these mg's can be cancelled out, which can give us an equation that said h minus mu d is equal to 5 over 2 mg, no, 5 over 2 r. This one's supposed to be capitalized, be careful. So now we can write the expression for h. The new h will be 5 over 2r plus mu d.